It's 19:05 in the evening, and Mark Williams is standing in line waiting for a drink inside the glamorous atrium of Hyatt Regency Hotel in Kansas City, Missouri. The band has just started playing Duke Ellington's Satin Doll, and the weekly tea dance is already in full swing. Above him, guests are leaning against the railings of three suspended walkways, looking down at the dancers below, and from the lobby floor, those walkways look elegant, almost weightless, as if they were floating through the open space. Then, through the music, Mark suddenly hears something else, a loud, sharp crack. For a moment, nobody understands what it means, but hidden inside those beautiful walkways lies a weakness, and within seconds, that weakness is about to turn this evening of music and dancing into one of the deadliest structural collapses in American history. Now, to understand why so many people were here on this evening, we first need to understand what the Hyatt Regency had been designed to be. Because this was not just a hotel lobby, it was a showpiece. The atrium had been specifically designed to feel spectacular. From the lobby floor, the ceiling seemed almost impossibly high, making the space feel almost open to the sky, where sunlight entered through skylights in the roof and the glass walls. This then reflected off the polished floors, glass panels and metal railings, filling the lobby with a truly bright and glamorous atmosphere. And crossing through that open space were the hotel's most striking feature, those three suspended 130-foot-long skywalks that I mentioned before. They spanned the atrium in parallel at different levels, one on the second floor, one on the third, and then one on the fourth floor, with the second floor skywalk hanging directly beneath the one on the fourth floor and the third floor one offset to the side. So from the lobby below, they created a dramatic layered effect, with people moving above one another, looking down through the open space, whilst others looked back up from the floor beneath. Architecturally, this was brilliant. It gave the atrium drama, movement and scale, and for Kansas City, that mattered because the Hyatt Regency had to be more than just another hotel. You see, in the 1970s, many American downtowns found themselves in serious decline. Jobs, investments and middle-class families had been moving outward for decades as suburban life became more attractive and accessible. One Federal Reserve study described US urban decline as having climaxed during the 1970s, with cities like New York, Boston and Chicago each losing more than 10% of their population during that decade alone. Now, for city leaders, the consequences of this were impossible to ignore. People were leaving, tax revenues were shrinking and investment was drying up, and that all created an urgency for downtowns to be made more attractive again. One answer to that were large integrated urban redevelopment projects. Hotels, offices, shops, restaurants and public spaces all connected into one carefully planned environment. And the Hyatt Regency was part of exactly that kind of vision. Now, it belonged to Crown Center, a major redevelopment project backed by Hallmark Cards through its Crown Center Redevelopment Corporation, or CCRC. And Hyatt's role was then to just operate and brand the hotel. Now, for Hallmark, this project was a public statement that they believed in the city's future, so the hotel had to do more than just provide rooms, it had to become a destination in itself. So, to make that a reality, they hired PBNDML architects, with their job being to design a building that felt modern and ambitious, which they also did. In July of 1980, only 1 year before this story took place, the hotel was finally open to the public, and it quickly became one of the city's most popular night spots. Every Friday, hundreds or even thousands of people would gather in its atrium for the weekly tea dances, which were old-fashioned social gatherings with live music and drinks. So on the evening of July 17th, somewhere between 1,500 and 2,000 people filled the atrium, and among them was Mark waiting in line directly beneath the suspended walkways. For a moment, that sound Mark had heard didn't make any sense. The band was still playing and people were still dancing, but somewhere above Mark, The fourth floor walkway had now begun to fail, and that noise was the sound of that top walkway, initially dropping just a few inches. Then, with a sickening sound, the entire connection holding the walkway in place began to rip apart, eventually setting the fourth floor skywalk completely free, and together the interconnected second and fourth floor skywalks and their 70 tons of steel, glass and concrete now came crushing down onto the crowded atrium below. For a few seconds there was almost no sound at all, just dust, broken glass and twisted metal, but soon the cries started. And by the end of this night, 114 people had lost their lives and another 216 would be injured, making this the deadliest structural collapse in the United States history. How could something like this happen inside of a brand new modern hotel that had opened barely a year earlier? How could the very feature designed to make it feel spectacular just tear loose and come crashing down? Well, to answer that, we have to take a close look at the structure that held those skywalks in place. You see, even though they looked weightless, in reality they obviously were not. Those walkways were supposed to be designed to carry tens of tons of metal, concrete, glass and people. And turning that architectural idea into a safe structure was the responsibility of the structural engineers. That role belonged to the company Gillum Colaco through its subsidiary Jack D. Gillum and Associates, a firm that would later become known as GCE International. Now, Jack Gillum was the engineer of record, meaning that he was the licensed professional whose authority stood behind the structural design, while Daniel Duncan was the project engineer, responsible for much of the day-to-day engineering work, and on paper, their original design had looked quite straightforward. All three walkways were suspended from the roof structure, with the second floor walkway hanging directly beneath the fourth floor one, and then the third at an angle, but that one won't be interesting in this story. In any case, the suspension system of these skywalks depended on a series of long steel hanger rods, each one coming down from the roof framing, and in the case of the two parallel ones, passing through the fourth floor skywalk and then continuing down to the second floor skywalk beneath it. But before we follow those rods, we need to understand what they were actually attached to. You see, the walkways themselves were layered structures. At the top was the carpet, beneath was a sand and cement layer used to create a flat and even surface, and below that sat a layer of lightweight concrete with a steel mesh embedded inside of it for reinforcement. Then, under all of this was a ribbed steel deck, supported by a frame of cross beams and span-wide stringers, but the most important structural members were the box beams that ran across the entire width of the walkway parallel to the other cross beams. Now, these were not solid pieces of steel. Instead, each one was made by taking two C-shaped steel channels, placing them back to back, and then welding them together along the top and bottom edges. That created a closed rectangular box shape, strong enough to act as a support beam, but still made from relatively thin steel sections, which is a detail that will become important later because the hanger rods passed directly through these box beams, meaning that the load from the walkway had to be transferred through the steel around these holes. Now, below the box beam, along each rod, was a large, thick rectangular washer plate, held in place by a nut threaded onto the rod. So the weight of each walkway pressed down onto its three box beams, and they then transferred that load into the washer plates and nuts. From there, the load then traveled into the vertical hanger rods, which finally carried it upwards towards the roof structure. You with me so far? But there was a practical problem with constructing this way, and that problem soon became clear to Havens Steel, which was the company responsible for fabricating and erecting all of the structural steel in the building. Now, the construction of individual components are obviously crucial in any type of structure, and as it turns out, that also goes for everyday items, and I think you know what I mean by that. You know that feeling of pure satisfaction when something you own just works and does exactly what you want it to do? Well, that's how I feel about today's sponsor, Exter, and especially their wallet, which I have been using every single day for over a year now. Exter also recently worked together with Messi, and I completely understand why. It is hard to find a more sleek, good-looking and functional wallet. It comes in a variety of different colors for both men and women, and with its pop-up mechanism you can get all of your favorite cards into one place. Awesome. It also has RFID protection to stop thieves from swiping your card details, and it comes with a tracker finder card that helps you find it if you would misplace it somewhere, either on the street or in your house. This is basically the perfect gift idea, either for yourself or for Father's Day, and Exter actually has a 50% discount for that up until the 24th of June, so make sure you use it. Now, Exter gives a lifetime warranty on their wallets, and they have recently released a new, slimmer one called the Wallet Pro, which I am really looking forward to try out. Exter also sells things like a super nifty vacuum bag that can give you up to 60% more space in your suitcase, and that's perfect for people who travel a lot, like I do. So to get yourself one of those, or an Exter wallet, scan this QR code or go to partner.exter.com/mentorblackbox to get an additional 20% discount when you use the code BLACKBOX. Thank you so much, Exter, for helping me continue to create this new channel. Now let's get back to the construction of those skywalks. You see, each hanger rod would have to have been a full 46 feet long in order to run the full distance from the roof down through the 4th floor skywalk and then on to the 2nd floor skywalk. In other words, each rod would have to span several stories of the atrium as one continuous piece of steel. Now, a rod that long would be very hard to manufacture and to transport, and would then be even harder to handle on site, whilst aligning it through 2 separate walkways during the installation. Then, on top of that, came the threading problem. For this system to work, the nuts and washer plates had to be positioned at the correct levels along each rod, which meant that the entire section of rod between the 2nd and 4th floor walkways would need to be threaded to allow those plates to be wounded into place. But threading long rods accurately is really difficult, and once the rods arrived on site, the threads could then easily be damaged while they were being handled, lifted and then fed through the structure. So, for the steel fabricator, this was not just inconvenient, it actually represented a serious buildability problem. Now, the design might have made sense structurally, but physically putting it together would be risky and time-consuming, so a solution was proposed. According to later testimony, William Ritchie, the vice president of Haven Steel, called up the project engineer, Daniel Duncan, with a simple solution. Instead of using one long continuous rod running from the roof through the 4th floor skywalk and then down to the 2nd floor, why not just split the system into 2 shorter rods instead? One rod could then run from the roof structure down to the 4th floor walkway, and a second would run from the 4th floor down to the 2nd floor skywalk below. From a fabrication point of view, this made perfect sense, since the rods would be shorter, they would be easier to manufacture, easier to transport and far easier to install. And it also removed the need to thread one very long rod across the full distance between the 2 walkways. So on paper, this change looked practical, almost harmless, but structurally it actually changed the entire load path. Now, an easy way to understand what this would mean is in the way engineer and writer Henry Petroski once described it. Imagine a rope hanging from the ceiling with 2 people holding onto it, one person higher up and the other below. As long as the rope remains continuous, each person's grip only has to carry their own weight, and that weight is then transferred into the rope and from there up to the ceiling. So the upper person is not carrying the lower person. Each person is supported by the same continuous rope. But now imagine cutting that rope just below the upper person and then tying the lower part of the rope to his legs instead. Suddenly, the situation changes completely. Now, the upper person is no longer only supporting his own weight, he will also be supporting the weight of the person below him, which subsequently means that his grip has to be strong enough to carry both of them. That was exactly what this proposed change would mean to the 4th floor skywalk connection. The The second floor walkway would no longer be sending its load directly up to the roof through one continuous rod. Instead, its weight would travel up through the lower hanger rod and then be transferred to the fourth floor box beam by passing through the washer plate and nut at the connection into the box beam itself, and only then into the upper hanger rod leading to the roof. So in short, this would mean that the fourth floor box beam would no longer just support the fourth floor walkway, it would now also be supporting the second floor walkway hanging beneath it. So the load of that connection would, with this, be doubled. Now in hindsight, this should have been obvious to any competent structural engineer carefully tracing the load path, but accidents like this rarely happen because of one mistake in isolation. Instead, they happen when several layers of protection all fail at the same time. And to those of you who watch my sister channel Mentour Pilot, you will already be familiar with this concept. It's called the Swiss cheese model. Imagine every safety barrier in a project as a slice of Swiss cheese. Each layer is meant to catch a problem before it reaches the people who could be harmed by it, but every layer also has some holes in it. Assumptions, time pressure, miscommunication, missing documentation, or even simple human error. Now most of the time those holes doesn't line up, so a mistake who passes through one layer then gets caught by the next. But in rare and dangerous occasions, those mistakes can keep moving forward towards an eventual accident. And to understand how this particular change now slipped through, we have to look at the way that the Hyatt Regency was being built, because this project was moving fast, very fast. The actual construction work was being handled by Eldridge Construction Company, which was the general contractor, and the hotel was being constructed using what is known as a fast-track process, meaning that its construction began before every detail of its design had been completely finalized. Now on paper this approach can save time, since instead of waiting for the entire building to be fully designed before starting, different parts of the project could move forward at the same time. This would mean that the design would continue, fabrication could begin, construction could start, and everyone was trying to keep the project moving. Now I have to point out here that fast-track construction is not normally unsafe. It is used all the time, but it does create a more demanding environment, since decisions that would normally happen in a slower, more controlled sequence now would have to happen under more pressure. This was a high-profile redevelopment project, and every month without an opening would mean more cost, more money not being earned, and more delay before the hotel could begin doing what it was built to do. But to fully grasp what happened after that change was proposed, we need to now follow the drawings instead. You see, a building like this is not built from one single set of plans. Instead, it's built through layers of drawings, and each layer has a different job. The architectural drawings show how the finished building was supposed to look and feel, and what kind of experience the building was meant to create. Structural drawings then show the skeleton. They specify the steel members, the hanger rods, the connection details, and the loads that the structure had to safely carry. So the architectural drawings show the vision, and the structural drawings show the physics to achieve that vision. But the structural drawings were still not the final step. The approved structural design was then sent to the steel fabricator, who produced shop drawings, and these were supposed to show how the approved structural design would be manufactured. So they showed the exact steel components, dimensions, welds, holes, rods, nuts, washers, and assembly details that the fabricator intended to make. Haven Steel, though, didn't prepare those shop drawings alone. With several projects moving at the same time, they instead outsourced that draft work to WRW Engineering, who produced the shop drawings for the walkway steel. Specifically, shop drawing 30 and erection drawing E3, which showed the walkways. And with that, the revised hanger rod arrangement was soon no longer just a suggestion from a phone call. It was instead being drawn into the documents that would show how the steel was actually going to be fabricated and installed. And that's where the danger entered the paper trail. But shop drawings obviously doesn't go straight from the fabricator to the construction site without review, especially when changes have been made. They were then sent back to the structural engineer, which was supposed to be the checkpoint where the engineer verified whether they still matched the structural design. So these revised drawings were sent back to the structural engineering firm as part of a much larger flow of shop drawings that needed to be reviewed. But in the demanding environment created by the fast-track construction, Duncan then viewed this change as a convenient fix to a buildability problem, not as a structural change. And he would later make that crucial admission that he hadn't really performed calculations on the revised connection before the drawings were approved. This meant that no one checked whether this revised design could carry the load it would be subjected to. Instead, the engineering review stamp was just applied to the drawings, and once that had happened, the revised hanger rod detail was no longer just an idea on paper. It was now approved to be fabricated, installed, and turned into the actual structure hanging above the atrium. The holes in the Swiss cheese model were now perfectly aligned. But what's actually making this even more frustrating is that this building had already given everyone a bit of a warning. During construction on October 14, 1979, part of the atrium roof suddenly collapsed, causing around 2,700 square feet of roof structure to come crashing down. Now, fortunately, the building was not occupied at the time, so no one was killed or injured, but this was obviously a serious event, so inspectors were called in to try and explain it. GCE themselves investigated it internally, and the owner also brought in an independent structural engineering firm, Seiden and Page, to try and figure out what had happened. Now, this could have become the moment where the entire atrium structure would have been opened up to deeper scrutiny, with every major connection being checked again, but instead, this investigation was given a quite limited scope. Seiden was asked to only determine why the roof had failed, to recommend corrective actions and to assess whether the construction could safely continue, but they were not asked to carry out a full review of the entire structure. And although the owner and architect also directed GCE to check the design of the atrium, including steel-to-steel and steel-to-concrete connections, Gillum's instructions were to limit the design check to the structural members of the atrium roof, while Duncan believed that all the atrium steel was checked. And since the roof failure was eventually attributed to construction stage issues like temporary bracing and erection sequence rather than a fundamental flaw in the permanent structural design, the project just continued, and the fatal hanger rod connection remained exactly as shown on the approved shop drawings, carrying double the load that it was supposed to take. And like I hinted to earlier, there were actually more problems with this design than I've already mentioned. If doubling the load on the connection point sounds bad, the reality was even worse. You see, these skyways were public circulation spaces, so the building code required them to support a specific live load, which is any weight that changes over time, like people, for example. In this case, the code required them to support 60 pounds per square foot, meaning that every square foot of walkway had to be able to safely carry 60 pounds of live load, on top of the permanent weight of the structure itself, which is called dead load. But the investigators would later discover that even the original single rod design was not as strong as it should have been. In fact, the connection holding everything up had only about 60% of the strength required by code, which meant that the design already had very little margin left in it. And that in turn meant that when the hanger rods were split, effectively doubling the load on the fourth floor connection, the final built structure had only about 27% of the strength that it was supposed to have. Let that sink in. About 70 tons of steel, concrete and glass had been allowed to be left hanging above the heads of hundreds of people, depending on a connection that had only about a quarter of the strength required by code. So why had it been so weak to start with then? Well, remember how those box beams carrying the walkways were not solid blocks of steel? Instead, each one had been made from two C-shaped channels welded together along the top and bottom edges, and that the hanger rod then passed straight through those box beams? This meant that a hole had been drilled through the steel at the very point where the load had to be transferred. So, as the walkway pulled downward, the washer and nut pushed upward against the underside of the box beam, carrying the weight into the hanger rod. Now, in theory, the washer plate was then supposed to spread that force across the steel, but in reality, far too much load was being concentrated around the hole, and the steel there was relatively thin. At a certain point, right as Mark and the others were waiting for their drinks below, the weld seam between the two C-shaped channels began to split apart. And once that seam opened, the box beam could no longer transfer the load properly into the hanger rod. So the connection eventually tore through, and because the second floor skywalk was hanging from that same fourth floor connection, it then lost its support as well, leading to the failure of both stacked walkways. By the time Mark and everyone else realized what was about to happen, there was no time left to escape. Within seconds from that initial crack, the skywalks came crashing down with terrifying force, crushing everything in their way. Some people were killed instantly, whilst others became trapped beneath the steel and concrete, calling out for help from tiny spaces that the rescuers could barely reach. And to make matters even worse, the lower parts of that collapsed chaos soon started filling up with cold water from burst pipes and fire protection systems, which threatened to drown all of the victims that had been pinned down there. It took rescue crews hours to finally get all of the different water sources turned off, and then with the help of cranes and hydraulic equipment, they could start reaching all of the remaining survivors. After more than 9 hours, Mark became the very last person to be pulled alive out by the rescuers from the wreckage, and the immense force of that collapse had dislocated both of his legs from his pelvis, so he ended up spending the following 2 months in hospital, where he survived kidney failure and then had to undergo intensive physical therapy in order to be able to walk independently again. Years later, a friend invited him to an event at the Hyatt, and when he stepped back into that lobby, he found himself drawn to that exact place where he had been trapped beneath the wreckage. He walked over, stood there for a while in contemplation, and then left, never to return again. He later said that the collapse had changed him. It made him value his family, his friends, and it made him see every ordinary morning in a way that he hadn't before. As he put it, we don't know what we can accomplish, what we can withstand until we are tested. Now, the National Bureau of Standards, today known as the National Institute of Standards and Technology, immediately launched a detailed investigation into this collapse. And they soon found no evidence that the collapse had been caused by defective steel or poor welding. The contractor had installed the walkways according to the approved drawings, and the materials themselves had met the specifications. So this made the investigators conclude that the change from one continuous to 2 separate rods had doubled the load on the already underdesigned 4th floor box beam connection, pushing it far beyond what it could safely carry. But with that also came some harder questions, like who was responsible? Civil lawsuits began almost immediately. Hundreds of victims and families sought compensation for death, catastrophic injuries, medical costs, lost income and permanent disability. And in the end, the settlements would total around $140 million, making it one of the largest civil settlements in the US at the time. But despite the scale of this disaster, no criminal charges were ever filed, so no one went to prison. Instead, the investigators and prosecutors treated the collapse as a case of professional negligence and gross error, not criminal intent. That absence of criminal charges obviously became deeply controversial, since to the victims and their families, the fact that no one had meant for the walkways to fall didn't change the result. 114 people had died, including 18 pairs of husbands and wives, with 216 people severely injured. And this failure had passed through professional hands before it ever became locked into steel. But instead of criminal convictions, the most serious consequences came through the professional engineering system. The Missouri Board for Architects, Professional Engineers and Land Surveyors eventually opened disciplinary proceedings against the engineers involved, especially focused on Jack Gillum and Daniel Duncan. and their findings were severe. The board concluded that the engineers had violated professional standards through gross negligence and unprofessional conduct. Gillum, as engineer of record, had carried ultimate responsibility for this structural design. He was the licensed professional whose seal and authority stood behind the project. And Duncan, even though he wasn't the senior figure, was also held responsible since he was the one that had reviewed and approved the revised shop drawings without performing the calculations needed to verify the changed connection. As a result, they both lost their Missouri engineering licenses, with the firm's authority to practice engineering in Missouri also being revoked. And together, that represented one of the most serious disciplinary outcomes in American engineering history. But the larger impact of this case went far beyond those individual engineers. This disaster changed the profession itself and helped sharpen the meaning of professional duty in engineering. It ultimately altered the meaning of review, since it showed that a shop drawing can contain a structural redesign, and when it does, it cannot be treated as routine paperwork. It has to be checked with the same seriousness as any other structural decision. It also clearly showed that connections are not just minor details. They are the parts of a structure where loads are transferred, concentrated and carried, and because of that, they deserve the same attention as the beams, columns and other major structural members get. But maybe most of all, the Hyatt Regency disaster showed that responsibility cannot be passed through assumptions. These skywalks didn't fall because they were defective. No, they collapsed because the load path changed, calculations were missed, and everyone responsible assumed that someone else had checked it. Gillum's firm argued that the revised skywalk suspension detail had come from Haven's steel and that they therefore bore some responsibility. But even though Havens should have understood what they were doing, that argument ultimately didn't hold. Gillum's seal made him responsible for the structural design elements he proved, and that precedent still shapes the meaning of engineering responsibility today. Now, I really hope that you found this video interesting, and if you did, remember to subscribe to the channel. You can also support what we do on Patreon by scanning this QR code or by going to patreon.com/join/mentorpilot. You can try that out completely for free, and I would love to see you there for my next hangout. My name is Petter Hörnfeldt and you're watching Mentor's Black Box. Have an absolutely fantastic day, and remember, every accident is a lesson. Bye-bye.